So my talk is on the evolution of callbacks. I'll discuss what are callbacks and in different ways callbacks can be implemented in C and C++. Well, I'm Umar and I'm the owner of Post Technologies and I'm the proprietor of Post Technologies and I've been delivering training programs on C++ design patterns for almost 2 decades now. In the past, I've worked predominantly on Win32, Windows, and Android. I've published a few games on Android. And I've also published some C++ courses on my platform at learning.post.com, Udemy, and O'Reilly. Nowadays, I predominantly train people on C++ and design patterns. And only thing I love more than C++ is modern C++. The objectives of this talk is to understand what are callbacks and how they can be implemented in C and C++, why are they important, what kind of problems they solve, and what modern C++ brings to the table. I'll start with basics of functions, and I would like to relate how I learned about functions. It was, I think, the winter of 93 or 94 when I saw a computer for the first time and somebody was playing a game on it. And that is when I was fascinated by computers. And I, at that moment itself, decided that I'm going to do something in computers. And at that time, we did not have internet and there was nobody to ask. There was no place from where I could get information from. The only place was books. So I realized that you can program computer by using some programming language. And I realized the good place to start is basic. So I bought tons of books on GW Basic and started learning programming on my own. The problem was that I did not have direct access to a PC. It was someone my dad knew, so I had to ask for permission, and then I used to write programs on paper and then type them down. And I got stuck at one point when I was learning GW Basic. There was this statement called go sub, and it was basically a function call, which it means that you jump to a subroutine. And I had a hard time in understanding why would we want to jump from this code to somewhere else. What is the reason? It took me a long time to understand what go sub is. You won't believe it, I did not understand it in GW Basic. I understood it later when I learned about C. So that was the first thing, my first tryst with functions. And then fast forward when I learned about C sharp and I had to deliver a training to professionals who were working in C++ and they wanted to migrate to C sharp. This was somewhere in 2004 or 2005. And then I encountered the concept of delegates. And I realized that it suddenly dawned on me that delegates is something that is very similar to what we have in C and C++, that is function pointers. I had seen function pointers in the past, but I really hadn't understood why we need them. I knew their syntax, but really did not understand them well. So when I saw delegates and what problems they solve, the book had wonderfully explained delegates, and they had also the authors had also explained something from the context of C and C++. And I got fascinated with the concept of callbacks. And that also started my journey in learning design patterns. So that basically triggered two things. One, my interest in learning about function pointers in depth and also design patterns. And so that's what now want to start from the basics, what a function is. We know a function is nothing but a block of code that contains some statements. Why do we do that? Because we want to modularize our application. We want to reuse that piece of code. A function is very flexible. It can accept arguments. It may return a value, and it can have a unique name. But we know in C++, a function, the same name can be shared among different functions. We know that is called overloading. Now, one important thing about functions is that when we invoke a function or when we call a function, the function call is resolved at compile time, but the function is invoked at runtime. Now, this is a very important concept because this will be useful in understanding the callback mechanism through function pointers later. So I would like to switch to Visual Studio and show you a small example. So these are a couple of functions that I have written. Typically, functions are split across multiple files. So basically, there is a header file, there is a implementation file, and the header file contains the declaration, and the implementation file contains its definition. So so in this case, I have four functions. You can see sum is a function that is implemented twice, but with different number of parameters. So this is simple function overloading in C++. And I also have a function template. Well, function templates, when you compile your code, function templates are just functions and nothing else. But there is some difference that I would like to tell you about in a minute. So here I invoke the function. This is how the function is invoked. How does the compiler know f is a function? Because the symbol appears before the function is called. If you do not have the function definition here, you should at least have the function declaration or prototype somewhere. Now, I assume that is there, or I have anyway defined the function here. So this is perfectly all right. And then I'm also invoking the square function. Square function accepts an argument and returns a result. And then I'm printing that result using printf. You might wonder why I'm using printf when we have cout in C++. There's a reason for that. Basically, I'll debug this code, and I would like to show you the disassembly. When we use cout, because of the way the names are encoded, and it becomes a little difficult to understand things in disassembly. That's why I've used printf here. And then sum is being called again with three arguments. Then again called here with 5 arguments. And then finally, I'm invoking max. The difference between invocation of a normal function and the function template. First of all, this max is just a template, right? It's not executable code yet. So when you invoke this max function, the compiler will instantiate it. The process is called instantiation. Basically, the compiler will generate a definition of max for integer types. That's what happens. And now it will be invoked like a normal function. That's all. So let's debug this. And I would like to open the disassembly window.
Umar, if these pop-ups are troubling you, you can go and mute them. Just open one and just mute that.
Yeah. How do I mute them?
There would be three dots right besides chat. You click on that, and then there would be a
Uh,
mute option.
I think it's from the other meeting.
Yeah,
Uh,
other meeting only.
yeah, it's from the other meeting, I guess. Anyway, it's not bothering me. It's all right.
Okay, then it's fine.
So I'll open the disassembly, and here we are. Now I'm more familiar with the Intel syntax x86, x64 disassembly rather than ARM. So I've chosen this platform to explain how things work. Because I've compiled my application in debug build, there will be a lot of debug information in the assembly, so we will just ignore that. So I will come down here, and this is the call to the f function. This is the instruction, assembly instruction that invokes the function. Right? This is the simplest function call, and we can even jump into it, and we will see it jumps to the function. And then it does something, the statements are executed, and then it returns. This function does not have any return value, so there is nothing to return. But then next, we see the call to the square function that is called here. And there is another instruction before it, that is the argument which is being passed to the square function. Now, depending on the platform you're using, the arguments may be passed differently. On 32-bit platform, the arguments are passed through the stack. So you might see for square function, you might see the assembly instructions push. But since I'm compiling in 64-bit, the argument is stored in the register and it will be accessed by the function from the register in the function itself later, right? The registers that are used may vary from compiler to compiler. All right. And then we see the call to the square function. And then the square function returns a result. The functions usually return the result in the accumulator register, which is EAX. This is the 32-bit register. If it's a bigger value, then it will be returned in RAX. All right. So the result is taken from EAX and it goes in the result variable. That's what happens. Okay, there's no magic happening here. If we go down and look at the call to the sum function, here you can see the arguments are stored in the registers and then the sum function is called. And we get the result from the accumulator. We go down, same thing. It has used some more registers. So this is how the arguments are passed into the function. And further down, there's a call to the max function, which is a function template. There is no difference. The function template, when it's after it is instantiated by the compiler and invoked at runtime, there is no difference. It's invoked normally. In fact, you can even see the call to the printf function. All right. Now, why did I show you this disassembly? Because I wanted you to see how the function is called. I mentioned in the slide that the function call is resolved at compile time. This is what it means. The compiler at compile time knows itself the name of the function that it has to invoke. Rather, that has to be invoked at runtime. So for all the functions that we're calling, we can see the names of the functions. This is important. Everywhere we see the names of the functions. So the functions are known to the compiler at compile time. And that's a good thing. Why that is a good thing? Because if the compiler can see the definition of this function, then it might be able to inline the function. So we won't have the overhead of, calling the function, preparing the stack, returning the value, destroying the stack. All that is not required. So this was how the function is called. Now the function can be used to implement a callback. What is a callback? A callback is simply some user written code which is passed to some other piece of code. And that piece of code will invoke the code that the user has written. Why do we do this? Why it is required? We'll see in a moment. So how is your user implemented code passed around? We create a pointer to the code to the function code through a function pointer. A function pointer simply points to a function which has been implemented. This is the syntax. It's very similar to how we write the signature of a function. The only difference is that we just have to use the parenthesis and declare a pointer. And this pointer is a function pointer. And if there are any calling conventions that the function that you want to point to has, you can specify the calling conventions here. Well, this was more relevant on Win32 when you were using Win32 APIs. On 64-bit, the calling convention is just cdecal. So let's see another example of how we can create a function pointer for implementing a callback. All right, these are the same functions. And now I want to invoke these functions through their addresses. So first of all, I declare the function pointer. The signature must match the function that you are trying to invoke. The signature must match exactly. And then to get the address of the function, you simply use the usual syntax, the ampersand. the address of operator. And to invoke the function, we have to dereference the pointer and use the parenthesis. But this is not the only syntax. The other way we can get the address of the function is by writing the name of the function. When we write the name of the function, it automatically decomposes to the address of the function. So ampersand is not required. And when you invoke the function, you do not have to dereference it. You can just invoke it like a normal function. Then I've created a function pointer to the sum function that accepts 3 arguments, and another function pointer that is pointing to some function that accepts 5 arguments. Is there going to be any ambiguity between the function that the pointer must point to? No, because we have specified the signature of the function during declaration of the function pointer. So even if the functions are overloaded, there is no problem at all. And down here, this is how I've created a function pointer to the max function. But then you might wonder, we have not invoked the max function yet for integer types. So what will happen here? A function template is instantiated when it is invoked or when you create a pointer to it. So just creating a pointer to max function is enough to trigger its instantiation. Because I have created 2 function pointers, the compiler will instantiate max for 2 types, one for integer, other for floating point type. If I am using auto, see, I could have used auto anywhere to create the function pointer. Maybe I could have used it here. And this would have also worked fine. There's nothing wrong with this. And we would probably save ourselves from the complex syntax of a function pointer. I can try doing the same here. But this is not going to work because the compiler doesn't have enough information about the type of the max function, for which type what type it refers to, which instantiation it refers to. So this is not going to compile. So either you give the full signature or you must yourself specify the type name. So I will specify the type name. Maybe I want to instantiate it for string type. So this will instantiate max for the string type arguments, and this will be a function pointer with the relevant parameters and the return type. Now, what is interesting is the disassembly of how the function is called through its address. So here we are. This is normal function call. Oh, I'm sorry. We need to switch to this project. So here we are. Where is the call to the f function? We don't see the name of the function anywhere. Instead, we see this instruction call and keyword ptr pf. What does this mean? This means get the address which this refers to and invoke it. So the function name doesn't appear here. And if we go down, even here, we don't see the name of the function being called. P square is the pointer that points to the address of the function. It is not the function name. So here the compiler doesn't know which function is invoked. And that's a great thing because we can leverage that thing. The lack of knowledge that the compiler has about the function that is to be invoked is useful. Nothing changes. The arguments are still passed through the registers. We still get the return value, but the only difference is the way the function is invoked. So this becomes a callback. Now we are able to invoke the square function without its name. And we will see the same thing for the invocation of the psum The function name is not used. We go down. Same thing for the other sum function that accepts 5 arguments. And if I'm invoking max, it will be exactly same. So this is the difference. The compiler doesn't know which function has to be invoked. So what are the advantages then? Where can we leverage this? First of all, it is it with this with function pointers, it is possible for us to create binaries that can call user written code. Normally, user written code calls some code in the binaries, maybe in the dynamic libraries or in the shared libraries or frameworks or static libraries, but this can be reversed. The binary can call the user written code. So this way, the user can customize some of the behavior of the binary or the library functions. So this all happens at runtime. So it supports runtime behavior. And just like with normal functions, these can be invoked. The function pointers or the callbacks that are implemented using function pointers can be invoked synchronously or asynchronously. What are the examples of such things being used in the standard libraries? The best example is at exit, the C function at exit. What does it do? It accepts a function address and then invokes, and then that function is invoked just before the program terminates. So that might be useful to perform different tasks, maybe clean up the temporary files, you know, and maybe dump the leaks that your application may have. Now you might ask, why do we need at exit? Why can't we directly call that function? Our application may have multiple exit points. So you may be calling exit from multiple points. So you just have to specify the function in at exit and it will be called automatically from the place where the application exits, even if there are multiple exit points. So that is useful. The other example is qsort, which is a C function for sorting elements of an array. So what kind of callback does it use? It uses a comparator that can be used to compare the elements of the array. In the same way, in C++, we can set a handler for new. When new fails, it can invoke that handler. How do we set that handler? Using set new handler function. And in the same way, for catching unexpected exceptions, unexpected exceptions in exception specification, we have set unexpected, but this is deprecated now and it has been removed. And then in operating systems, we have functions that return pointers or they work with callbacks. For example, get proc address, it's used in Win32 to get the address of a function which is in the DLL. So the DLL is loaded at runtime and the functions that it has, we can get their addresses at runtime and invoke at runtime. That is a very powerful mechanism. Then if we want to execute any function asynchronously, we can use create thread. Create thread is used for creating a thread and that thread executes a user supplied function. And in the same way, we have winproc, which is the Windows procedure, which accepts the events generated by the windowing system. And we have DLSIM, which is analogous to getproc address, pthread create. All of these work with function pointers. But then there are some disadvantages. There are some things that you have to be aware of. First of all, the function pointer is just like any other pointer. So there are no compile time checks. It is impossible to figure out if the pointer points to a valid function. Therefore, if the address is not valid, it can cause a crash. Because the function is invoked at runtime, because compiler doesn't know about it at compile time, the compiler may not be able to inline it. That is why its invocation as compared to a normal function may be slightly slower. It's also not object oriented. So I cannot extend the functionality of a callback. And the functions, because a function pointer points to a global function, it cannot store state. All right, then what alternatives we have? And why do we want to store state in a function? Well, that's required in many places. Then what about member functions? What if I want to create a pointer to a member function? You cannot create a function pointer to a member function because a member function is not a normal function. It has a hidden parameter, which is the this pointer. So that's why we have to create a pointer to member function, and we call it PMF. And PMFs are not as common as function pointers, so they're used in special cases. All right, so this was, I'll come to PMFs in a bit. So this is an example of where I have an array and I want to know the index of the element in the array. So this accepts the array pointer, the size of the array, and the element. And then I search for the element in the array and return the index if the element is found. Otherwise, I return -1. But what if I I want to perform a comparison in a different way? Maybe I want to find an element that matches a specific criteria. I don't want to do an exact match. Then how do I do that? I can use a function pointer. So the function pointer can be passed as an argument in a function and then can be invoked here. So what I have done here is I've modified the find custom to accept a function pointer. And then the function pointer is invoked here. So this is a callback. And in this particular case, the function that this callback refers to, the pointer refers to, returns a bool. So it is a predicate. And find custom can be now customized to match elements based on any criteria. So here the criteria is, give me the first element that is greater than 6. So I can just pass this function pointer and it will return the index of the element. Or I want to find the first even number, the odd number, or an element within a specific range, I can do that. I just have to write a new function.
Umar, you are on mute.
I don't know how that happened. Maybe while, oh, I think it was because of space. Uh, I think it was the teams were selected and space. I wrote some code, so I went on mute.
Okay.
Apologies. So what happened here was I wanted to find an element within a specific range here. So I wrote a new function in range, and then without modifying find custom, I was able to get the element that falls within this range. I did not have to modify find custom. So that's a great thing. This means find custom can be put inside a binary and we never have to modify it. And we can still customize its behavior. And I have some more
Umar,
examples.
there are a
Yes.
couple of questions on chat. First one was some long back. Tilak is asking, doesn't the argument passed to the function depend on the ABI?
Well, in this case, in case of the functions that I'm using here, I'm using C calling convention, right? That is one. And secondly, I'm compiling on x86 platform. So within that platform, the ABI is going to be same. There is not going to be any incompatibility. But if you have compiled a binary, let's say you have compiled a library using, let's say, Intel compiler, okay, or maybe GCC compiler, and then you have a client which is compiled with MSVC compiler, then in that case, there's going to be a problem, right?
Okay. And the second question is, can we use callback mechanism to create an event loop? I guess Stack Overflow will need to be solved.
Yes, we can use call. We can, in fact, the Windows message loop uses callback mechanism. It does that. So it doesn't. There is no question of the Stack Overflow being happening, because in case of the Windows message loop, it's written like this. So message, get message, and then we have some arguments, and then we have translate message and dispatch message. This is, I've just ignored the arguments, but this is the Windows message pump. This is the event loop or the message loop. So what happens is when there is any event in your thread that has created your UI, the event will go to the thread's message queue, and get message will retrieve it. And then dispatch message will dispatch it to the corresponding event handler. So after the event handler is executed, the thread returns to the message loop. So there is no question of the Stack Overflow, because it returns to the caller. The thread returns to the loop. It continues. I hope that answers the question.
Yeah.
Okay. So here I was invoking the function sum and diff from operate. You can see sum and diff are defined below operate. So operate has no idea about sum and diff, just like we saw with find custom. So this is just another example that demonstrates that the function using the function pointer, we can invoke any function as long as the signature matches. We have seen function pointer as a parameter. We can also return a function pointer from a function. This is an example. Slightly more, a slightly different example. The only thing is that I'm taking the index from the user, and then that index is used in this conditional set of conditional statements, and it returns the address of the function based on the user input. The syntax is a little complex. So you can also return function pointer from a function. We can simplify it further, especially when we are returning function pointer from a function. And you know what I'm talking about, using type def, or even better, using alias, C++11 alias. So I can simplify my return type using this alias or the type def. And I also prefer using auto here. But auto might not always work in case you are returning a different type. Maybe you have written default, or I'm not throwing an exception. I'm returning a null type. In that case, auto is not going to work, because all the return statements must be of the same type. In that case, I can use the trailing function syntax. So I just have to specify the type of the pointer, which is int, star, int, and int. So these are just alternative ways. You can choose one over the other. So this was usage of function pointers, but as I mentioned, it doesn't store state, and it's not object oriented. So the next thing we have, the next best thing we have is pointer to members, pointer to member functions. And Here, the pointer to member function is the syntax is very different than what we are used to in C and C++. And I have tried learning about pointer to member functions many times, and every time I used to forget the syntax. But this is the syntax. The pointer to member function must have the name of the class along with it. And just that is not enough. When you invoke the member function when you invoke the member function using the pointer to member function, you also need an object. So that is something that we I will share the entire code with Dheeraj. It will be available for download. So you can just share the code right
So,
away.
we'll upload that on GitHub, CppIndia GitHub. So, and we'll share that link as well. No problem.
So this is how to invoke the pointer to member function. This is when we have an object. When you have a pointer, the syntax changes. These are other two operators that cannot be overloaded in C++, apart from the regular ones. And what about static member functions? Well, static member functions are just global functions in disguise. They just have the name of the class attached to them. So when you create pointer to a static member function, it is just like a normal pointer, function pointer. It's not different. All right, great. So we have seen how we can create pointer to member functions, but where are they useful? They're not as powerful as function pointers because I have this button. Maybe this is a UI button, and when the button is clicked, this click function is called, and I would like to handle that click event. So I have created the frame class that has on button click, which must be linked with the button click. How do I do that? The problem here is when you invoke a pointer to a PMF, you need the name of the class. So this button class cannot be put in a binary because it will depend on the name of the frame, and frame is a user class, or it can be implemented somewhere else. So this becomes a limitation. But these have been already used for implementing events in many UI frameworks such as MFC or WX widgets. So how do they implement it? So this is the same example, but this time what I have done is I have created a base class called base frame. And the PMF uses the name of the class, the base class. And we remember when you invoke a PMF, you also need the object. So the constructor of the button accepts the handler, that is the PMF, the pointer to member function, and the object. And then it is invoked here. All right. Now the question is, when we have to set the handler in the constructor of the button, how do we do that? Because so this is my frame, okay? And just want to show you this directly. If I pass the address of the on button click directly, it will not work because the type is different. The type here is the button click implemented in frame class. And the type here is a PMF of which has the scope of base frame. So this is not going to work. So what do we have to do is typecast it, which becomes ugly. So that's why I created this macro, which takes the handler name and automatically applies the typecast. This is precisely what MFC does. When we add an entry in a message map. If you have worked on MFC, you'll know we specify events using message maps. So this will work. So when the button is clicked, it will call the function. And this works. But then we have an alternative to this. There is another alternative that we have. Instead of using PMFs, there is another alternative. And let's see what that is. So one advantage that member functions have over function pointers is that they can store state. So that is useful. That means the objects can be serialized and I can load them and invoke the PMFs later. But it's not that simple. All right, because not only you have to store the PMFs, you also have to store the corresponding objects. But it is possible. Because of this, PMFs are not very flexible because both the object and the type are required during invocation. So we saw that with the button example. The frame name is required for the button to invoke the PMF. So it's not very flexible. And again, because it's a pointer, it may not be type safe. So what do we have then? Well, we have a very wonderful feature that can replace PMFs, and that is the virtual functions. What are virtual functions? Well, I would say they are just PMFs in disguise, but they are a little more sophisticated. And the compiler helps us here. So what we do is we mark a member function with the virtual keyword, and then you know the rest. All the virtual functions are stored in a table called virtual table. It's an array of virtual functions, the addresses to virtual functions. And then these virtual functions can be overwritten. And then how do we invoke them? Well, there is no special thing that you have to do in order to invoke them because the compiler automatically generates the code. So there's not much to see here because this is something which we use a lot in C++. So this was our earlier example that used PMF. Can we convert it to use a virtual function? Yes, it's simple. All we have to do is just create a virtual function called on handle event. This can be optionally pure virtual. Let's not forget virtual destructor. And then this is not required. This thing is not required. And we can just invoke the function like this. Becomes very simple. The only thing now this button needs is the address of the object that implements on handle event, which can be our frame. So I will just use override here. Override, and we need to ensure that the name of the function is same. And this ugly syntax goes away. This is much better. So we don't have to deal with the typecasts. And I don't have to discuss the internals of how this happens. That is taken care of automatically by the compiler. The compiler generates some special code. And I would like to show you how it is internally invoked. And you will see something very familiar there. If you look at the disassembly, there's something very familiar here. What is this? It is the call that has been generated by the compiler. Call to what? Call to a function based on its address. So virtual functions are nothing but function pointers internally. And there's some more sophisticated code here that gets the address of the function, gets the virtual pointer, and then calculates the offset and then invokes the function. This is type safe because the compiler checks for the function signature. At the invocation place, at the invocation site, the code only has to know about the base type. So this promotes extensibility because I can add more derived types. This is more object oriented. Because it is It uses classes, objects, it can store state. But the runtime invocation may be slightly slower because again, it's a call through the address and there is some time spent in the lookup. And if you have too many virtual functions, that will increase the size of the virtual table. So this is the reason why in MFC, they did not use virtual functions. It would have been just much simpler from the user's perspective, but they went ahead with PMFs for handling events because they found out that because there are so many events and for hundreds of events, you will have to create hundreds of virtual functions and the size of the vtable would increase because the vtable is a static array which is stored in the data section of the executable. The size of the executable will also increase. Remember, we're talking about early 90s when we do not have powerful computers. We do not have ample amount of RAM. So this was a concern. Now in modern systems, this may or may not be a concern, depending on the kind of application you're creating. So this is another way we can implement a callback. But then C++ gives us one more way, and that is the function object. What is a function object? It is an object that has a user-defined function call operator. And the syntax is very simple for invocation. The function call operator is invoked just like a normal function. Because of this syntax, it can be used as a replacement for function pointers as callbacks. And you know that it is heavily used in the standard library. So the function object can be implemented like this. This is a struct fn, and this is the overloaded call operator. The interesting thing to see is how it is invoked. It is invoked like a normal function. And you must have seen this syntax if you would have generated random numbers, or if you would have generated hash of a number. To generate the hash of a type, we use a function call operator. So it has multiple uses. But one thing I want to show you is how it is invoked. That is very interesting. So I'll keep a breakpoint here and here we are. And if you look at the disassembly, the compiler knows which function is invoked. It has the knowledge of the function that is invoked. And that's a great thing. Why that's a great thing, we'll understand in a minute. But can we use the function object for our find function? Can I do that? Yes, I can do that. So this is my my find custom. It accepts the function object that is check-in range, and that function object is invoked here. This is the old find function. We'll just focus on this find custom. But then this is not really flexible, right? It is not very flexible. Why is it not flexible? Because the type has to be known. So that is something that we have to take care of. Can be taken care of using a template. After I convert this into a template, the find custom doesn't have to know the exact type. So the check-in range is implemented before find custom. So it has no idea about check-in range type. So it is able to invoke this as a callback. So this is very useful. Extremely useful. Further down, I have changed the find algorithm to use iterators, just to be in line with STL, because we are more used to that. And this is a better function because it will work with not only with arrays, it can work with any container that has the notion of iterators. So Here we are. But what do we get out of this? What is the advantage? Because a function object is a class, it can store state. So if I want to find an element in a specific range, if I want to find an element in a specific range, I can create instance of check-in range and initialize it with some data. So this is stored as a state, and this state is accessible here when the object is invoked. So this state is available here. This is impossible with function pointers because they are global functions. They cannot store any state. In the same way, I want to find an element which is greater than a specific value. Again, I can create a function object that can store a state, and I'm using it here. So this is the advantage, the primary advantage of function objects. What if I were to use function pointers? Then this is a global function. I cannot parameterize 5 and 10. It's impossible. Don't even think about using global variables here. That will hold the range values. No, we won't do that. Although there are other ways using templates. So this is the primary advantage of using function objects. They can store state, but there is something else that we have to see, something very important. So what I have here is two functions, start fn obj, that uses function object as a callback, and start fn that uses function pointer as a callback. And I want to show you what happens at this point, how the function pointer and how the function object is invoked. And then we will go from there. So let's debug this part first. So this is for the function object has reached here. Let's add the breakpoint here. All right, it has reached here. And if we look at the call of the function object, you see it's the call to the function call operator in check-in range. So compiler knows which function is invoked. Compiler has complete knowledge because since this is a function template, the compiler has instantiated it with all the necessary types. It's come out. The same thing is applicable to find custom. Compiler will know. Now, what I'm interested in is this find in this start fn, which uses function pointers. All right, we have reached here, and let's go back to this site that will invoke the function pointer. And in this case, you see the compiler has no idea which function is invoked. All right, but this has a side effect. Using function objects versus function pointers, what to prefer? If both give you the same thing, suppose I don't want to store a state, what would I prefer? Would I prefer a function pointer or a function object? Then this will help you out. So I'll again start this debugging. So we have reached here in start fn obj, and let's look at the find custom function call. This is the find custom function call here. Can you see the type? It is an example for namespace, and since it's a template, these are the type names. The type name is int star ptr64 and check-in range. This is the function that is instantiated. And is that a problem? No, it's just the function is instantiated. But if we move down and look at the function call for find custom with greater than, Here it is. The second template parameter has a different type. Because it is a different type, the compiler has instantiated find custom twice for two different types. So that means there are two definitions of find custom. So this is something you have to keep in mind. This means if find custom is invoked with 10 different function objects, there will be 10 different instantiations of find custom. Is that a problem? I don't know. You decide that. Okay, what else? What about invoking the function, invoking the function pointer? All right, here we are. And this is invocation of find custom when we are using function pointer as a callback. Let's go down. And here we are. This is the type that the compiler has instantiated. Is it different than what we saw earlier? Yes, it is different. The second type is not the function. It is the address. It is the signature. It is a pointer type. And if we go down and see the invocation of find custom for greater than, when the callback is greater than, what is the signature? It is same. This means when you use function pointer as a callback with such functions, with function templates, the function template will be instantiated only once. And that function template, that instantiation will work with any kind of function that you pass as a callback. So is this an advantage over usage of function objects with templates? You decide that. Are you okay with multiple instantiations of the same function when different function objects are used? Are you okay with that? Then there's no problem. If you're not, then you might want to consider using function pointers. So we have seen how function objects are invoked versus function pointers. So what is the advantage of using function objects? They're resolved at compile time. So compiler knows at compile time what is the type. So it is type safe. Because the compiler has the knowledge of the function that is to be invoked, it may be inlined. So that is why it is faster than a function pointer while giving the same behavior. And best of all, it can store state because a function object, well, it's an object. It's an object of a class. So it can store state. But then, as we just saw, the template will be instantiated for each unique function object that you pass as an argument in the template. And secondly, when you specify function object as an argument, or if you store it somewhere in a template, you cannot change it at runtime. Function objects with templates, the way we have seen here, are fixed at compile time. You cannot replace at runtime. That is possible only if you use function pointers. But this is not the only way to create callbacks. There is one more way that we can use. Here is another example, slightly more involving, but what I've done here is created an object pool. So basically what this pool does is, basically in some kind of applications, you don't want to create a lot of objects. You might want to reuse objects that are not being used because that saves the cost of the repetitive cost of allocation and deallocation and also prevents the fragmentation of the heap. So that is why I have created this this example. So this is how we use it. So here I've created an instance of object pool for strings. I get the object. Basically, I request the pool to give me an object, and then I assign some name to it. I request the pool to return, give me another object. So it will create a new object. And then I no longer need the first object. So I will release it back to the pool. Next time, when I request for another object, the pool will return an existing object. So I have used some logs here. I'll enable them and we'll see the output. For the first two objects, you can see a new object has been created. But after I returned the first object to the pool and requested a new object, it returned a pooled object. So this way I have saved the cost of allocation and reallocation. All right, after I do this, I realize that I may have to use my application, my object pool in a multi-threaded application. So this is my multi-threaded usage. Okay, so there are multiple threads that are using the pool. I'm not revealing the code yet because there is something that I'm using which I have not discussed. So let's run it. Anything can go wrong. So it seems to have crashed. The crash is somewhere over here. So it has crashed. Obviously, we know why it has crashed. It's quite obvious. It's because we are using the same object in multiple threads. What if I want to make it thread safe? Well, I can easily make it thread safe by using a mutex. I just have to use a mutex, apply a lock here and a lock at the end, and apply a lock here and a lock at the end. I can do that. That's not a big deal. The issue is if I do add a lock here and a lock at the end, what if this class is used in a single threaded application? Then even in single threaded application, the thread will unnecessarily acquire the lock and release it. So I don't want that. What I want is some way through which we can specify from outside whether it should apply a lock or not. So again, we need some callback. So users should be able to specify whether we should lock or not, depending on whether the object pool is used in a single threaded or a multi-threaded application. So can we use function pointers here? Well, not really, because we need to store state. We will have to store mutex. We'll have to store the state of the mutex across several calls. So I cannot use function pointer. Can I use a function object? Maybe. But there is a limitation of the function object that we are able to call only one function. I cannot overload the function call operator with the same signature in the same class. That's another limitation. So what do? I can rely on good old templates. So what I'll do is I will create the object pool with one more template parameter. And this is the lock policy. An instance of the lock policy will be created, and we will use the lock policy. We will use the lock policy to apply a lock here. And I'm using lock guard so that the lock can be released automatically. And I'm doing that here and here. And right now, the lock policy that I have specified is no lock. What is no lock? No lock is a default lock policy, which doesn't do anything. It doesn't apply a lock. All right. So if I use the object pool with the default lock policy in a multi-threaded application, so this is my multi-threaded application that uses the object pool in multiple threads. What is going to happen? The default lock policy is no lock. No locks are applied. Crashed. So I realized, oh, I'm using this in a multi-threaded application. So what should I do? I should specify a policy that applies locks. So I create a class called mutex lock that has the same interface that is required by the object pool. But there is no base class. You can see it doesn't inherit from anything. So there is no virtual mechanism involved. So it's going to be fast. So I just specify mutex lock here. And what will happen is during the construction, during the compilation, object pool will be instantiated with mutex lock. And this will be mutex lock. And internally lock guard will call lock on my class, which will internally call lock on mutex. So without having to use function pointers or function objects, I have implemented a callback using templates. Is there going to be a problem if my interface doesn't match? There is no problem. Because I'm using templates, the checks will be performed at compile time. So there is an error. It's a compile time error. So it says lock is not a member of this mutex lock. So there is no problem. Even without using base classes, I can ensure type safety. And guess what? Because I'm using templates, when I compile this code in release build, and lock guard will internally call lock on m_policy. Basically, I'm just calling that directly here. And we know that this lock is a method or a member function implemented here. The compiler at compile time knows lock is a method of this class. So can it inline it? Yes, it can inline it. So it is possible for the compiler to replace this entire line with the internal implementation of the mutex. So this becomes fast. Well, if I'm implementing this in Java or C#, then I have to use the runtime behavior using virtual functions. And there, the calls will be at runtime. Where is this used? This is used in many places in C++, in many libraries. The best example is the allocators in containers, or when we specify a comparator in a set, or when we specify an equals, or the hasher in unordered containers, or in many frameworks. For example, in ATL.com, we do specify something like this using template. So we have something called threading model. So we can have single threaded model or multi-threaded model. So we specify those using class names. But then there is something that C++11 brings to the table, and that is Lambda expressions. What are these? These are unnamed function objects, basically just syntactic sugar. A shortcut way of creating function objects. And these are also called closures. When we use a Lambda expression, the compiler automatically generates a function object, but it is much more than a simple function object because the compiler generates something else. A function, the Lambda expression may be stateless or it may be stateful, and it is useful as small callbacks. So we use function objects a lot. So here is the example of a function object. You remember how in the previous example, I was using the function object here. I was using it here, the function object here. And the function object was defined somewhere else in a different namespace. So I was creating a class in a namespace because I want to use it here once. With Lambda expressions, you don't have to do that. All you have to do is just create the Lambda and pass it as an argument into the function there itself. This is really wonderful because I don't have to pollute my namespace with new names. This is no longer required, right? And the same thing I could do for find custom. When I want to find the element, first element that is greater than 3. And there is something else here. This lambda expression is stateless, doesn't have any state, but this lambda expression is stateful. It has a state. It is capturing the environment, its external environment. So it has a state. I don't want to go into the internals of how lambda expressions are implemented, but these are just function objects, and the compiler generates them for us. So this simplifies a lot of work for the user, for the programmer. Remember this object pool that I had created. I used findif, which is same as my find custom was implementation of findif. So what it does is to find the object in a pool, it iterates over all the elements and invokes this function object, check available. What does check available do? This is the implementation of the function object. What does it do? It accepts the pooled object and checks if the available part is true. Basically, it is just a struct. The object and whether it's available or not, that's the information it holds. So I created the function object here. This increased the size of my class. I also had to create one more function object for this loop, which I use in release. So how do I release? How do I know that the object is no longer used? I will first find that pointer in the list of pooled objects. If it exists there, I will mark its availability as true. Okay, how do I match it? By using this function object match objects. I could have easily replaced this thing with a lambda. Yes, I've done that here. In this case, I don't need match objects and check available because I'm directly using the lambda here. My code is more expressive. I don't unnecessarily create new types. And specifically, I needed this only once. I don't need this implementation in other parts of the application. If I do need, then I will create a function object, a regular function object. But I don't need, so I created a lambda expression. And I did the same thing in release, where I was earlier using a function object. This can be further improved, but I have used object pool in many of my games where I wanted to ensure that I don't repetitively create new objects. So this was quite useful. And this can be improved even further. So finally, I would like to mention about some utilities that C++11 and other newer standards have introduced. We have these function wrappers. We have a std function, which is a function wrapper, which is very useful in case you want to invoke a callable. What is a callable? A callable can be a function, a member function, a function object, a lambda expression, or it could be a function pointer. It largely simplifies the invocation of a callable. If I have to create a class that has to invoke any kind of callable, then instead of using a template or a function pointer, I would prefer to use std function because it allows me to invoke any kind of callable, which can be a global function or even a member function or even other std function. And sometimes when we have to invoke a function, it's signature doesn't match with what we have. In that case, we can use a binder. So binder simply converts a function with n parameters into a function with n minus m parameters. But Lambda expressions have sort of taken over the functionality of bind. So what bind does, we can do the same thing using Lambda expressions. And personally, I find bind to be very confusing and difficult to teach because of how it has, you have to use placeholders and you have to use them in the right order. So it's quite confusing. To invoke member functions easily, the pointer to PMFs, if you create a PMF, you can use memfn, which can help you invoke PMFs. And C++17 introduced something else called invoke, which is just like std function. But the difference is that std function stores a callable. Invoke simply invokes a callable and is less, it is faster than std function. But std function and invoke serve different purposes. And this finishes my talk.